Okay, great. Yeah. So let's start with recapping the slides from last lecture that we didn't finish. And this was in particular IMU spoofing part. So before we talked about GPS spoofing, and now we're talking about another type of sensor that's being spoofed, IMUs. So what was the good thing about the GPS spoofing part is that essentially it was somewhat easy to spoof in the sense that we are talking about digital signals, communication signals that are received by the GPS receiver that are then being decoded, demodulated, and then based on the time of arrival of these signals, the location estimation would be done. And spoofing GPS then requires you to essentially send out correctly modulated GPS signals. But there's, of course, all kinds of other sensors in a drone that mostly don't rely on digital communication signals to find their sensing values. And IMUs are one of these examples. So what were the IMUs again? These were the inertial measurement units that you have quite a lot in drones that, for example, for 6 axis can give you accelerations in different along the 3 axis and just where you are in space. And then also these rotations around the 3 axis. These are the 6 axis sensors then. And I'm just going to use this as one example for sensors that are really measuring physical properties, acceleration along different axes. And now we're getting really into kind of the physical layer manipulations of such sensors. So how could you now try to remotely have an impact on the readings of such acceleration sensors without actually physically accelerating the whole drone into that direction? So this is more to, again, raise that there are potentially interesting manipulations here that are non-trivial to think about or to discover. So there was a nice paper. The first paper that I'm aware of that is talking about manipulations of such IMUs is the Walnut paper. So this waging doubt on the integrity of MEMS accelerometers. So the idea here is, so first of all, if you're interested in these kind of physical layer manipulations of sensors, there's a couple of researchers on these papers that are really doing work in this domain for a while already, and that we'll see more often as well in the citations that I will give. This is in particular Wenyuan Su and Kevin Fu. Wenyuan is, I believe, still a professor at CJU in China, Zhenjiang University, and then Zhenjiang University. And Kevin is in the US. Kevin has been doing research for quite a while in this domain as well. And he at least used to be for a while also be responsible for medical device security from kind of the federal government perspective in the US. Anyway, so Wenyuan and Kevin have been doing a lot of research in this domain for a long time already. So what was going on in this paper here? They looked at a specific type on how you could realize accelerometers, and in particular with these MEMS accelerometers. So how are these working? So how do you in general measure acceleration? Yeah. So how these work is that they actually have a little movable sensing mass that is mounted in along a specific axis with a spring. And then this has essentially one part of a capacitor mounted to it. And then the other part of the capacitor is fixed mounted to, let's say, to the sensor or something like this. So what happens now is if you're starting to accelerate such a accelerometer along the axis here of the springs, then the sensing mass will, of course, move into one direction or another direction due to the acceleration. And this will change the overall capacitance of this component, which you can then measure electrically. So the capacitance is that translated into a voltage, and the voltage is being measured, and then you get a value over time, which is essentially relating to how far away this mass is pulled from its neutral position against the force of the springs. And then you have this for all the different axes, and then you get your 6-axis accelerometer. So how could you now try to manipulate this remotely maybe you saw it from the title of the paper already. So their idea was now to kind of have an impact on the readings of this accelerometer, not by accelerating the whole component or the whole drone, but rather by using acoustic waves essentially to then have tiny impacts that influence the sensing mass and accelerate the sensing mass through these acoustic waves and not through moving the whole drone. So the idea is very simple. Yeah, you have speakers or whatever, something that is giving you these physical waves, audio waves, that will then also move or impact the sensing mass, and this will have a change, lead to a change in the capacitance and then a change of the voltage. So just to give you one idea of what kind of interesting manipulations could be done in this space, yeah. Of course, what you get out of this is, first of all, it's not an attack where the attacker can precisely just say, okay, I want to now have the following acceleration coming out of the accelerometer of the victim. Yeah, it's relatively imprecise, let's say it like this. And it's also something where you might want to have kind of constant acceleration or something like this. It's a little bit unclear on what kind of input signals you would need to send as an attacker to get certain output signals out of the accelerometer. Of course, in addition as well, the range of this might be quite limited, or I don't recall how much they investigated the range in this year, but the range might be still relatively short. They discussed it in the context of a drone as well, but then of course all the experiments were not done on a flying drone, but in a lab setup somewhere. Yeah? But how does it overall work? They found that, for example, if the accelerometer is measuring in this example here a certain vibration, so there's a 70 Hertz vibration going on, which normally, if measured by the accelerometer, will result in a signal like this. They then added an acoustic signal with a certain frequency of much higher than 70 Hertz, so 2.9 kilohertz. And then they activated the signal for a certain duration, 300 milliseconds or something like this, and then they deactivated it for 300 milliseconds and so on. And then the resulting, the effects of the acceleration that was shown off at the output of the accelerometer would then look a little bit like this. Yeah? So here you'll see in the phases where the attack is not being active, you get a signal that roughly corresponds to the actual true acceleration. So in those phases, in those 300 milliseconds, the sensor will still give correct values. And then in the other phases, it will give, first of all, higher acceleration values. And in addition, the frequencies might also be very different to before. So now we get seeing an overlap of these two signals here. And so from this very simple experiment, you can already kind of understand that, first of all, it is possible to have an impact on the overall readings that are coming out of the sensors. But of course, now as well, if the sensor would now suddenly see a signal that has, that has an acceleration with a very high frequency or something like this, maybe the drone might not even care about this. So we have to somehow see what is actually the ultimate effect on the drone if we somehow provide now input values to the sensors that are outside the normal scope of the normal physical properties that we're measuring. And this is what the authors investigate here a little bit more with, essentially by looking into what is actually happening in this receiving and processing chain at the drone. They found that, well, they have three different ways how accelerometers could be constructed. They have like the ideal theoretical accelerometer where you have the mass that is then generating the signal that I explained. And then you would amplify the signal to make it easier to measure because it might just be a very weak signal. And then you would, in the signal processing, probably apply a low-pass filter, this LPF here. And this low-pass filter is then something where anytime you get analog signals that you're measuring and you have a certain idea on how the signal should look like that you're looking at. Maybe you're just looking for slower changes in the signal, the lower frequency components of the signal. You use a low pass filter to essentially filter out high frequency noise that might be on the signal. So you filter out this noise and then you recover relatively low frequency components of the signal. And then this could, for example, give you now your 70 Hertz signal. If the real devices might not, just be implemented like this. They might, for example, have what the authors called here an insecure low-pass filter. So it could be a filter that is not really cutting off high-pass, high frequency noise or something like this. And then when you have the signal coming in, and there are high frequency components, they could still be present later after the filtering. And then as a result of the tech, you get these kind of fluctuating measurements because there are relatively high frequency components still in the signal that are now part of this 2.9 kilohertz signal that was injected by the attacker. And you would get readings out of this that essentially will change over time. Or you could have also a problem in the implementation where you have what they call an insecure amplifier, but which is any typical realizable amplifier usually looks like this. If you have an incoming weaker signal out of the accelerometer that needs to be amplified before it's being measured, then amplifiers typically have an operational range, and they will amplify incoming signals by essentially just making it 2 times stronger or something like this, but then the signal might eventually reach a signal level that is too high. So, and at that point, the signal will essentially cap out. It will be limited to the maximum value that you can send out here. And then this will distort the overall signal afterwards. If you do this amplification and the input signal was essentially too high, the output of the amplifier will be distorted. If you then do a low-pass filtering, then the resulting signal will also be distorted. So you might know something like this, for example, when you are maybe listening to music or something like this, and you are increasing the amplification, the volume level of the music by too much. At some point, the music will sound distorted, because essentially the signal levels are capping out, and you are starting to change the frequencies that are in the music. And this is what's happening here as well in this kind of, if you have these realistic insecure amplifiers, then an attacker might start to, just by increasing or by sending in a lot of energy, the attacker might start to cap out these signals. And then after you do a filtering on this, you will get signals levels that are not constant low anymore, something like this, but they will have a constant offset, which will then allow the attacker to kind of start to bias their outputted signal by quite a bit. Although all the high frequency components of the attacker are being filtered out by the low pass filter, the impact that the high frequency components had in the amplification will still be remaining as a constant offset here. So this is in the end how the attacker, these are the effects that could be achieved here. If there's an ideal accelerometer chain, and the attacker is sending on in these kind of audio signals in the frequency that is much higher than what is normally expected by the drone, then these high frequency noise should be rejected by the drone or the sensor. But if the filter is imperfect, then some of it could remain, but this will lead to a signal which is not very predictable by the attacker because it's just fluctuating at the receiver. And what they found essentially, what the easiest way for the attacker was to get a constant shift was to have this kind of relatively strong signal before the amplification that would then lead to this nonlinear effects here in the amplifier, which then remain even after the low pass filtering. So in the end, there's a couple of other papers that we'll talk about later by the authors, but the main idea is often that you can influence a sensor with signals that are theoretically not supposed to be able to influence the signals because they are of a different frequency. But due to constraints on how these things are implemented in the end, you might still have an unexpected effect. And in this case here, this would allow the attacker to impact the accelerometer readings. Yeah, so this is more to just raise the issue with you, and we'll dive into this topic later in the term again a little bit more, but it's just to give you an impression on how these manipulations could be done. Yes, question? Yeah.
The third scenario, attackers would an attacker would actually try to feed the sensor with fake signals. The most viable way would be to just raise the amplitude to get a distorted computation.
For the attacker, yes. From the attacker's perspective, they found that the most reliable way to do this manipulation would be to inject signal with high enough power that would then, or audio signals with high enough powers that have strong reactions in the accelerometer, and these strong reactions then lead to a constant bias in the end in the measured, in the measurement that is coming out after this processing changes.
Okay. So the attack would consist more in raising the amplitude rather than changing the frequency itself.
Yeah, I think in this case here, I forget how much they varied the frequencies, if they also tried other frequencies, but essentially, so the underlying assumption is that this low pass filter might cut off after 70 hertz or something like this. So at really low frequencies, and these low frequencies will be very difficult so without going into this too much at this point in the lecture, but different frequency bands usually can have properties that they are easier or harder to transmit, or they might propagate differently. Yeah? So these very low frequency audio signals, for example, they might be much harder to send over the air to a target. They might travel better through, buildings or something like this, but they don't propagate it well over the air. So that's why the attacker would potentially choose a frequency like 2.9 kilohertz, which is more or less around the range where human language or where humans also talk or something like this. So there's then potentially much easier hardware to transmit this, and maybe the transmission range is better for this frequency. Yeah? So I don't think that this precise 2.9 kilohertz matters here, but it's a frequency that is 10 times, 100 times higher than what normally should be accepted by the target.
Thank you.
Okay. And yeah, there's some limitations. I think I mentioned this already, but if you're interested more in these manipulations, have a look at the paper. There's a couple of follow-up papers by the authors as well. And I'm not saying that this is, the most realistic way that you can now start to immediately manipulate your neighbor's drone or something like this, but it is certainly an interesting interaction between, acoustic waves and this accelerometers. And having said this, I'll now switch to the slide set for today. If I can manage. And then we're going to start talking about countermeasures, how you could potentially, or maybe you have some ideas as well on how such manipulations like the GPS manipulation and the sensor manipulations could be detected. Yes, I'll skip over the first ones here, or, well, still one thing that I want to mention here is, yeah, we're going to talk about detection or mitigation. And one important point is, so we are always, of course, we're kind of switching between the offensive roles and the defensive roles. And we're doing this partially as well to understand what, as a defender, what are realistic assumptions that you could have about an attacker. And this is something that I'll come back a little bit more in the rest of the term as well. But in cryptography or traditional security, you often assume an attacker that knows essentially everything about the system except the private keys. And the attacker might be able to freely interact with any messages that are being sent out, suppress messages, inject their own messages, and so on. some people call these kind of cryptographic inspired, very strong attackers, these kind of Dolev-Yao style attacker models. And the question now is, should we have do we need to assume such a very strong attacker as well for attacks that somehow involve the physical domain? So should we now worry about attackers that can inject arbitrary acoustic messages to our drones that are flying high in the sky? Or do we need to worry that attacker might be able to manipulate any of our messages while we're transmitting them over wireless communication? Do we need to worry about attackers that have 100% precision, precise control over how their manipulations arrive at our victim? Or are there any kind of any constraints that we can realistically motivate, maybe with the laws of physics, on what the attacker could actually do in practice to limit the impact of the attacker, and maybe find countermeasures that might not protect against the strongest ever attackers, but that will help against most of the realistic attacks, for example. Yeah, so this is where we need to understand a little bit how difficult is it actually to do certain attacks, so that we can then also see, what kind of countermeasures are effective in making the attacker's life harder without potentially preventing with 100% all possible attacks. When I introduced a little bit earlier the structure of how drones communicate and how the sensors are positioned in such drones, so we could have different points where sensors on drones could be manipulated. We could somehow the attacker could try to directly manipulate the physical way that the sensors are reading things, or measuring things. So this is essentially this A attacker would be, for example, this walnut attacker that is doing the acoustic signal attacks on the IMUs, or it's the GPS attacker that is manipulating the GPS signals that are being received by the GPS receiver. You could potentially also think about an attacker that is manipulating the sensor chips themselves somehow, maybe due to a supply chain attack, or somehow locally the attacker can reprogram the sensors to behave differently. Or you could have an attacker that is manipulating the sensor readings between the sensors and then where they're being processed. Or you could have an attacker that is manipulating the way that the sensor readings are being processed on the controller and the way that they are, being used to now compute the control actions on the drone in the real-time operating system. So I'm pointing out these different cases just so that we are aware that there's all of these are somewhat related. You might think that all of these 4 different cases will have, in the end, the exact same outcome. But I think it's still worth to differentiate between these models or these cases in specific scenarios, and I'll come back to that later. There's subtle differences here. So, for example, you could assume that an attacker that is manipulating the input to the sensors, that attacker might not have fully precise control over what the sensor output is in the end. Or an attacker that is, doing a supply chain attack might have precise control over what is the output of the sensor, but maybe that attacker might have trouble somehow synchronizing these outputs with what else is happening on the drone or something like this. Yeah, and then it's also a remote attacker cannot just arbitrarily easily change the result of a compromised sensor, and so on. So there's a bunch of more subtle differences here that we'll get to in a little bit. Okay, so whenever I'm talking about attacks, I'll try to mention something like this again, or you can also think about what kind of different attackers are we talking about this now. So let's start with we had a lot of discussion about GPS. And I introduced also the paper that we wrote a while ago on the GPS manipulation, but now maybe someone of you could close the door. Thank you. Now the question is, how could we attempt to defend against such GPS manipulation. So I said before, GPS itself, cryptographically, it's unauthenticated. It's not surprising that it can be manipulated, but how could we try to detect such a GPS manipulation or spoofing? Yeah, anyone has an idea? And of course, I have keywords here already, but maybe I don't know if they will help you out. Maybe before we go into my suggested keywords, anyone else has an idea first on what you could do to maybe detect such a GPS manipulation? Yes? Okay, yeah, maybe yeah, you can. So your suggestion was the Kalman filter. This is the filter that you're talking about? Kalman filter? Yes. Okay. So use. So, but then, okay, can you just explain a little bit more? So, what would the Kalman filter do, or how would it enable us to detect potentially a manipulation?
It will try to, based on other measurements, sensors, it tries to estimate a new position
Yes.
and then compares it with the GPS readings and tries if it's too
Yeah,
far off.
it will check for consistency in these potentially related sensor readings. It might also do a prediction based on the past evolution of this parameter, and will do a prediction on where the next parameter should be. And this is, I mean, if I should simplify it a lot, then of course, what is the best way or the easiest way to predict what the weather tomorrow is going to be? Anyone has an idea on how you can easily predict, or what a simple predictor is for the weather tomorrow? If I just ask you, yeah. Oh, that's already, you need to understand a lot.
The weather today.
Yes. So I would just say, the most simple predictors are often just, extrapolate from today. Yeah, you just need one value for this. And in many scenarios, if you're tracking variables that are moving relatively slowly, I'm not saying that weather is always moving slowly, but I mean, a fair estimate of the weather tomorrow would be, it's the same as today. And this will already get you somewhere with respect to just randomly guessing any temperature tomorrow. Yes?
We talk about GPS spoofing, where we then maybe deviate from a pre-planned route. We could pre-compute expected acceleration values in certain directions. And then based on the new acceleration values, which might be induced through GPS spoofing, try to see whether there's a spoofing attempt because of the deviated movement from the drone.
Yes. So, okay.
Which is
so this could be an idea. So what you would say is essentially you would pre-compute the acceleration, like let's say before you even start the mission, before you take off, you would have a pre-computation of all the values and then compare against this. Yeah, you could do this. I have the suspicion that this will perform relatively poorly in practice because you get lots of false alarms, because probably even without manipulation, the real missions will quickly deviate from whatever you predicted in advance. Yeah. But in general, yes, maybe with more looser parameters or something like this, you could do a prediction like this. Yeah. But as well for GPS, I think the simplest prediction would just be, is the new reading by some threshold further away or further than some threshold away from the last reading. Yeah, just doing the difference between the new reading and the last reading, having some kind of threshold for what you expect as the maximum movement within one time step that should realistically ever happen, and then you might be able to detect large jumps already. Yeah, this is this kind of stealthy spoofing that I introduced last time already. that is a very reasonable, the most basic way essentially to detect whether you might have issues if you just do a simple comparison with the previous values, and if the difference is too much, maybe physically impossible, then it might not be correct. Yeah? This is often called a bad data detector. We're going into that also later in the term. The most simple way, just this computing this difference, and then yeah,
This would assume that the attacker must be really stealthy.
Sorry?
This would assume that either the attacker must be really stealthy and change just ever so slightly, or that the measurement is such that the effectiveness of attempted spoofing to stay undetected is ineffective for some purpose of an attacker.
You mean only in those cases would we be able to defeat the attack?
Yeah.
Or yeah, I also get a little bit into that more. So maybe before I really answer the question, let me say, so now we're talking about countermeasures here. And in general, I guess for countermeasures, we can differentiate between detection of attacks and actually mitigation or prevention of attacks or something like this, yeah? Or maybe even three things: detection of attacks, then mitigation, so not really preventing the attack, but mitigating the effect of the attack. Or the third stage would be, fundamentally preventing that the attack can happen at all and that there's any impact ever on your system. The prevention is relatively difficult, often with these kind of cyber physical system attacks that we're going to talk about. The detection is the easiest, for example, through those bad data detections. The mitigation, so trying to reduce the impact of the attack, is something that then where it's more interesting to also for the research to look into. Yeah. So for what you said now as well, for so you could say if you have a very good, and then the question is a little bit, if we have, okay, let's say with the most simple is the detector. The question now is what is actually happening after we have a detection? What is the impact or what is the result then? Because just detecting a manipulation might not enable a drone to then really carry out its mission or something like this. Yeah, we have to see what is then the next step after such a detection. And that plays now into whether the attacker wants to be stealthy or not. So maybe in some scenarios, the attacker might not care about detection, and they just care about having a certain effect on the drone. If there is actually consequences to being detected and we have some decent detection scheme, then and the attacker knows about this, then really we could start to force the attacker into being much more careful with these stealthy manipulations, limit the impact that the attacker can have within a certain time slot, and then this will potentially not prevent any manipulation by the attacker, but it might reduce the impact that the attacker can have, or it might just prevent overall any bad outcomes. It is fundamentally quite difficult here to kind of guarantee that there is zero impact of any attacker action on your readings or your mission. But maybe you can also tolerate minor manipulations, minor offsets, and so on, as long as you can still carry out your overall mission. So this, I mean, it gets a little bit philosophical here, but again, that's the difference then to maybe cryptography, where you would say, okay, I have this 1 gigabit file that I want to send, and if one bit out of the 1 gigabit is manipulated or impacted by the attacker, then it's invalid and I have to throw it away or something, yeah, because the signature doesn't compute anymore, and the signature doesn't tell me which bit was flipped. In these cyber physical systems, typically you would not self-destruct a drone if there's any minor, manipulation suspect or something like this. Yeah, it's you likely want to keep operating as good as possible, even though there might be an ongoing manipulation. And that's where it gets a little bit difficult again to decide what to do and so on. Often, and we saw it with the drone manipulation paper already, an approach that might be taken then is to try to switch into some fallback mode in the drone where maybe you're not operating as optimally anymore, but you can still at least recover the drone, for example. Okay, sorry, I talked a lot already, and I said we wanted to actually finish the slides. Let's see if that works. So what do we have here as suggested detection for GPS spoofing attack? So there are some earlier works as well that talk about more like cryptographic inspired ways to detect the GPS manipulation. So for example, for attacks, I talked about GPS manipulation attacks that actually would change the data content of the GPS signals. You could try to detect such manipulations by, for example, getting a delayed signed version of the current GPS signals over the internet or something like this. Just a copy of the signals that were sent by that satellite with the exact values, and then some cryptographic signatures applied from someone. And then you could receive this in addition to the true signals, and then just check if the values are the correct ones that were actually sent out by the attacker. Of course, it doesn't do anything about the time of arrival. There are some other delayed authentication schemes as well, but I'll not, go into these now in detail. A quite popular approach otherwise is the signal integrity checks. So this is something where it might be that when we start to switch on our attacker signals, that our attacker signals have much higher signal strength, for example, than the legitimate signals, because the legitimate signals are coming from a far away satellite in space, and our attacker signals are coming from 2 meters away or something like this. So you might consider tracking the incoming signal strength of the satellite signals. And then if there's too large of a jump of the signal strength, you could say, okay, again, physically, this shouldn't be possible to get such a strong signal from the legitimate satellite due to the known distance and so on. So I suspect an attack is going on here. And then there might be checks such as the angle of arrival. So RSSI refers to the received signal strength indicator. So very roughly, this is like when you check your Wi-Fi strength and you have 3 bars or something like this. This is something like RSSI. Yeah? Angle would then, if your radio somehow is a way to estimating from which direction the signal is arriving, you could track this and you can verify that the angle from which you are receiving your satellite signals is actually corresponding to where the satellite should be roughly. Or you could for sure also test if all the satellite signals are coming from exactly the same angle. You might suspect that they're all being spoofed by one antenna by the attacker. Noise monitoring, we'll get more into that later as well, but there you can also try to see if, for example, the noise that you're experiencing on the channel is what you normally expect to hear, or if there's a very high noise level, for example, if there's a lot of energy signals on the channel, that could potentially indicate, for example, that someone is trying to suppress legitimate GPS signals. So we're not going to go super deep into any of these, but there are papers and actual products as well. I'm sure out of all these things here, the signal integrity checks to some degree might be implemented in products already. At least I talked about to people about implementing this, 10 years ago or something like that. Yeah? So the detection of the attack start is, we also talked about this already. This is kind of tracking the location and trying to detect jumps and so on. And also the RSSI to some degree is related to this. And then the last one is actually multiple receivers. We are also getting into that. Yeah, so actually I do have slides on some of these topics now, but I think I talked about content already. RSSI, okay, we have it here. Plausibility, angle of arrival, consistency. We had these, yeah. So we will need to monitor these. I talked about this just now. And the last thing here, the multiple receivers, this requires a little bit more introduction now. So it is a very simple countermeasure, but why it works, I need to explain a little bit more. So we had, when I introduced the GPS spoofing, I said in a very simple setting, the attacker would have one antenna, and over this one antenna, the attacker will send out all the spoofed satellite signals. So they like the 4 spoof satellite signals will all come from one location. And as a result of this, the actual location of the victim will not really, the computed location of the victim will not really depend anymore on the actual location of the victim. If we have multiple victims in range of this one attacker antenna, because all the satellite signals are now coming with the same relative time offset, each victim will actually compute more or less the same location as a result of this. Yeah? Typically, the victim, the receivers of GPS should compute different locations because the satellite signals from the 4 satellites are all kind of arriving at slightly different relative time of arrival at the victims or the receivers. If we have one spoofing antenna, then all the signals will always arrive with the same relative offset at each of these receivers. They will all compute the same location in the end. So there is a second way how the attacker could run this. The attacker could actually start to use multiple antennas, for example, one antenna for each spoof satellite, and only then each receiver would receive a different or compute a slightly different location in the end. So we call this in the paper the group spoofing problem. Yeah. The question would now be, is there a way to arrange the antennas for the attacker such that the locations that are computed by the victims will also result into a computed formation of the victims that corresponds roughly to their physical formation. And what do I mean with formation? I mean that if in the real world, somehow we know that the first receiver is 2 meters away from the second receiver, and then the second receiver is 2 meters away from the third receiver, and so on, they are maybe set up in a circle or in a square. Is it possible for the attacker to somehow find locations for the antennas and delays for the signal such that all the 4 victims will also find themselves spoofed to some kind of specific location on the choice of the attacker, while still being in this exact formation of being in a square of a certain side length? Yeah. Yes, question? Or can you pass back the
So, in the simple scenario, the problem you underlined was that the attacker signal would arrive with the same time offset for each victim.
Yes.
So, therefore, they would compute all the same.
Yeah, I actually have a figure for this. Let me just jump to that maybe. But yeah.
Okay. And in the advanced scenario where there are 2 antennas, wouldn't the time offset also be the same still, even if you would have more than?
Yeah, let's just say, okay, let's just consider 2 satellite signals. Let's just say 2 satellite signals are enough to compute your location, okay? And let's say one of the attacker's antennas is on the other side of the victims, and so one is here and the other one is here. Yeah. So in that case, then, and the upper antenna here sends satellite signal 1, and this one is satellite signal 2. So in such a scenario here, the victim 3, for example, would get the satellite signal from satellite 2 first, and afterwards it would get the satellite signal from satellite 1 because it's just further away.
Mhm.
For the victim 1 here, it would get the satellite signal here from satellite 1 first, and then the satellite signal from satellite 2. So the relative time offset is different. Was that your question? Or,
Yeah.
I have this figure here. I know this is not immediately trivial to understand, but this is an important point here. So let me just try to explain this here again. So what I try to show here in this figure is left is the non-attack scenario. And here we have 2 receivers, and the first receiver here on the left-hand side receives first the satellite signal from satellite 1 because it's just closest. Let's just assume all the satellites send their signal at exactly the same time somehow. Yeah? So the satellite signal 1 is arriving first, then satellite signal 2, then 3, then 4, just relative to these solid lines that we see here. And at the receiver 2, it's exactly the opposite because, it's closer to 4 than 3 than 2 than 1. Yeah. So here we have now 4, 3, 2, and 1. Okay. And in the case of an attacker spoofing with a single antenna, then we have something that if multiple satellite signals are sent from one antenna, then there is a specific order in which they're essentially being sent out, just which relates to the location that we want to spoof. And at the second receiver, also the same relative offset of signals will be received just as a slightly later time. So that's why the second receiver will compute the exact same location, because actually this relative time offset of the signals determines the location. And if we now would have a second antenna, we would essentially come back to this scenario. So in some sense, you could also see this as a scenario where the attacker has 4 antennas somehow placed around the victims and sending out 1 spoof satellite signals over each antenna. And then you have the same setup here again. So roughly you have inverted order of arrival here again, and you can see that roughly the locations are going to be different that are going to be computed by the receivers. Okay.
Thanks. Clear now.
Okay. Yeah, so what we wanted to know now, essentially, so now why do we care about this? Because here, maybe you see already, so for this simple scenario, what can you already see here? What is the problem for the attacker if something like this is happening? Can we see already how this could be used for countermeasure by the victim? I'm not saying it's trivial, but to see. But this was 1/4 of the paper that we wrote back then.
So what's the question?
The question is, if you have this simple antenna, single antenna attacker, and we know that as a result of these things, both receivers will compute the same location, how could this be used to detect a GPS spoofing attack?
Both receivers could compute the time difference between the different signals arriving. And if they are equal, then now it's spoofed. And if they're different between the 2 receivers, it's not spoofed or not necessarily spoofed.
Yes. Yes, I think Sarah also mentioned something similar in the chat just now. Yes, we can compare the relative time difference of the signals between the 2 receivers. Or even similar than this, we can just compare which location was computed by receiver 1 and which location was computed by receiver 2. And they will essentially be identical in the attack case. And in particular, if the victims know that they are not at exactly the same location, but they're maybe 5 meters apart because, they have mounted at fixed, location on the car or something like this, for example. Yes?
But can actually assume that the receivers interact with one another.
Okay, yeah, but here, okay, fair enough as a comment, but yeah, let's assume they can communicate. So if the 2 receivers are somehow communicating, and if they have another way to knowing a rough estimate of the true distance, then they could use this. They could do just a comparison on the locations that they computed, which refers to the relative time offset, or which refers to the expectation of what the relative time offset should be differing between the 2. But in the end, the beauty here is a little bit that essentially, if you have 2 receivers that, for example, might be we always give the example of mounting them on a shipping container or something like this. Yeah? You have 2 GPS receivers that you're mounting on different corners of a shipping container. You know the exact physical distance between these GPS receivers. You only need to now look at the computed location, and if the computed location is identical or within a very small bound, then there's a relatively high likelihood that GPS spoofing is going on by such a simple attacker. Okay. And the beauty here is that we don't need to do any signal processing and comparison of the signal. We don't need to compute RSSI or anything like this. We just have to do one very simple location comparison that is cheap to do, with digital data, of course. And we also don't need to change our receivers at all. We just buy 2 commercial off-the-shelf receivers and just compare the result that's coming out here. So this was essentially one of the main insights that we had in the paper, which I found at least pretty cool. Maybe academically then not so cool, but for real life, I think this was pretty relevant to just realize this again. These most simple attacks, which are likely going to be the vast majority of all GPS spoofing attacks are going to be done like this, they can just reliably be detected with such a comparison of the location that's being computed. And now for the paper, we wanted to have some guarantees that this can now not be tricked by multiple antennas by a very skillful attacker. And I'm just going to very quickly outline how we try to do it in the paper. We essentially then started to compute for specific problems. We started to compute on what are the potential placements for the antennas of the attackers such that they have a given relative offset for the time of arrival of the victims. Yeah, and you get into, let's say in 2D, if you have 2 victims and you want to make sure that the signal from the attacker's antenna has a specific relative time offset, then you get this hyperbola as a potential placement, for example. Yeah, you can place the antenna anywhere on this hyperbola, and then the relative time offset of the signals at the victims will have a specific value. Yeah, this is just, okay, these numbers or the colors are just now indicating for different target values for the relative time offset. Yeah. And the intuition is that for 2 victims, you can still get a hyperbola in 2D, or in 3D, you would get actually, so for 2 victims, you get actually a hyperbola each in 3D, I guess. So a shape where the attacker could place the antenna to send out signals with the correct relative time of arrival. But now if you try to do this for more than 2 victims, for example, for 3 victims, the potential locations where you could place your antennas is essentially the intersection of 2 hyperboloids. This is then a hyperbola again in some plane in 3D. And if you want to do the spoofing on 4 or more victims, and you want to ensure that their location is, their formation is exactly preserved, then in the end, for 4 victims, you get essentially an intersection between some hyperboloid and a hyperbola, which is just intersecting at most 2 points. And these 2 points are essentially, one is the location of the satellite as it would be relatively in space. Yeah, so if we assume that the attacker antenna can't be in space, then this is infeasible for the attacker to put the antenna there. And the other location is then typically the same distance away, just on the other side of the Earth or something like this. Yeah, so our argument in the paper was then a little bit, if you set up at least 4 receivers in a fixed location, a fixed formation, then an attacker, even a perfect attacker that has, that knows all of this, it will essentially be impossible for the attacker to find the location to place the antenna to really spoof your receivers reliably. Okay, this was more like a theoretical argument that we're making here, and we did some more practical follow-up on this work on this in later papers. So the idea is here that even the stronger attackers with multi-antennas can't break countermeasures than if you're using 4 commercial off-the-shelf receivers in the formation. Okay, so the simple countermeasure was this 2 receiver countermeasures. We went over this already. And the 3 or more receivers is then the more, advanced countermeasure. And I guess the remaining question that we had when we wrote the paper was, 2 questions actually. One is, how far should we actually now do we need to place the receivers to get reliable detection results, not too many false alarms? And the other one is, okay, how does it play into moving victims and so on, for example, and how much control would the attacker, or how much leeway has the attacker with respect to noise and so on. But let's not go into that now. So for the placement, how far apart the receiver would need to be placed. For this, now we need to understand essentially what is, if you would set up such a fixed formation in absence of an attacker, just in normal operations of the satellites, what is the normal noise that you would have there and with respect to the locations? And what is the probability that by just having normal noise, you end up having 2 or more receivers in the end showing identical locations? Yeah. So this is what we investigated a little bit more in a follow-up paper from 2016, where we did a lot of experimental work. We also did some theoretical work trying to understand more what noise sources actually influence the location estimation or the location fix that you're getting out of GPS. And we realized that a good amount of noise on your location that your receiver is computing is actually due to effects like clouds and so on, and your immediate environment. And as a result of that, if you have multiple GPS receivers that are somewhat co-located, a good amount of their location error will also be co-located because the signals are essentially experiencing the same clouds and more or less the same path as well. Yeah? So if you have, if we then did some experiments, for example, where we set up 4 receivers in some formation, and we tracked over time so they were in a fixed location, and we just tracked how they moved over time and then plotted the relative distance over time as well. And we could see that there was some correlation there, that some of these errors would be lower for all of them at the same time. And in general, we could observe that they moved also in a correlated fashion. Yeah, so that at some point in time, they might all move a little bit to the left, or they might all move a little bit to the top, and so on. Yes, question, comment? Yeah?
With co-located receivers, is it meant that they are at the same height, for example, or?
Yeah, so just to, in this experiment, they were at the same height. Yeah, so this is essentially how I don't know if you can see too much, but this is just some benches that are set up somewhere, and then we just mounted the GPS receivers on these benches. They are in a fixed distance to each other and at the same height, yes. And with relatively same channels here. This was line of sight to the satellites to some degree. And the point was that then by understanding this noise more, we could then see how far they would actually have to be set up to reliably give us kind of spoofing detection. And there's these kind of figures that we have then in the paper where, let me see how I can explain this quickly. You see here the kind of histograms or the distribution of the calculated distances between the pairs of receivers. It's a little bit hard to read here the numbers, but they are not all at 0, because here the actual distance between the receivers might have been 8 meters or something like this. Here the actual distance might have been 12 meters or something like this. But you see that then over time, the measured distances based on the location fixes is relatively tightly around the actual distances. Yeah. And in the spoofing scenario, so we also actually practically send spoofing signals in the setting here. And you will then see that the mutual distances all became very small, all below 50 centimeters. Yeah, so the average was then 30 centimeters or something like this. So in the spoofing cases, you could really then see that they were not exactly at the identical location, at least not all the time, but they would all then find locations that were within 30 centimeters of each other, while normally they would be 12 meters apart or something like that. Yeah, and now based on this, you can kind of see, how close could you move them together. Essentially, what you want to have is that these red curves, you know, that they are not starting to overlap. Yeah, so you can just imagine here that we have the case of the spoofing is somewhere here on the left, and then if you would reduce the distances between the receivers, you would move this distribution closer to 0. But I think we concluded in the end that a distance of about 5 meters between the receivers would be sufficient to have, with a very low false alarm rate, this kind of detection mechanisms. Yeah, so then, for example, if you really worry about very strong spoofing attackers that might want to change your location fix, then you should set up at least 4 receivers in a fixed formation at a distance of at least 5 meters, and you should be fine, at least with the detection of this. Yeah? So this could be used, for example, for airplanes or boats or shipping containers and so on. This is what we talked about. Yeah, so 5 meters might not be enough for a car, but anything bigger than a car might be interesting. Yeah. Unfortunately, we didn't patent this. I think there's companies selling these now, but we should have really patented this as well. Any questions or comments on it? Yeah, so again, yeah, sorry.
The question for the height of this red curve, which is the probability density. I did not.
Sorry, what do you mean?
So you observe this red curve.
Yeah, the red curve is actually an approximation of, this is the fitted distribution towards the blue observations.
Okay.
So the blue thing is the histogram of the true observations, and then the red thing is a fitted curve, essentially. But this is somewhat the estimation or the expectation of the distribution of these differences between the.
Okay. Yeah. Yeah.
Yeah. This is not something that's theoretically predicted or something like this. This is what we truly observed in these experiments that we did. Okay, any other questions or comments? Okay, so this is a specific, this is somewhat, again, for the specific GPS case, just the motivating kind of countermeasure here would be that by thinking about a problem hard and by also doing practical experiments and so on, also on the attacker side, we realize that there are actually means to relatively cheaply detect GPS spoofing with commodity devices, essentially. And while initially we thought it's impossible to secure GPS or secure GPS in the sense of even detecting manipulations, we found that really, if you really care about this, it would be possible to build a reliable countermeasure. Yeah? And now let me go a little bit more into the maybe a generalization of this, of countermeasures that we also see more in the rest of the term. And some of these we have already mentioned as well. So in general, we're talking about this physical control loop again. I think we had this before already in this lecture. We, at the moment, talk about, so we have the physical process here that influences our sensor readings. The sensor readings influence the controller influences an actuator, and the actuator influences the physical process. Right now, we're kind of exploring this kind of attacker here that manipulates some of the sensors, either by impacting whatever is measured by the sensor, by changing the sensors themselves, or by changing the values that are sent out by the sensors to the controller. We will later see similar countermeasures as well that try to detect the other cases here where the attacker is somehow impacting the control actions or the actuation actions. Yeah. So how can we now, for the sensors, what could be general countermeasures to verify that, or what do we actually want to verify? Yeah? So what is the property that we want to verify out of the sensor reading somehow? So in crypto again, in crypto, we want to verify somehow the integrity of the data. And this might be, maybe we want to verify for a message that the timing of the message was not changed by too much, that it's, you know, that it's fresh or something like this. And maybe want to And the typical thing we want to verify cryptographically is that all the bits are exactly as the source had sent them. For sensor readings now, it is more difficult to talk about such an integrity because the sensor reading itself might, for example, be noisy. And many different things might be influencing the actual value that is being measured, at least very depending on your precision that you have, yeah? So just verifying that the value that is arriving at the controller is exactly the value that is happening in the physical world. This is not going to happen because the sensor will never give you exactly the 100% precise value as it is in the physical world. Yeah? So somehow we have to now find terms to talk about, what do we actually want to verify? And a concept that was proposed by some people here is the concept of veracity. So the veracity here is supposed to be described that the sensor reading is truthfully describing, the physical process without being influenced by an attacker. I'll not go super deep more into veracity, but there's a whole discussion of this in the paper that I'm linking here. And now the question is how, because in the end, for the control system, we care about that the physical property is within the expected precision of representing the physical process, and it was not manipulated too much by an attacker, such that we can still do our control action computations and then control our system. So how could we try to verify that the readings that we're getting are still close enough or truthfully represent what normally would be measured? So cryptographic signatures, I already tried to convince you that this will be difficult because, the thing we're measuring physically will not give us signatures. Yeah. So if we're measuring, let me give you a different example. Let's say a very simple sensor might be a sensor that is measuring, that is in a room and trying to detect smoke or fire even. And now, how can we ensure that this fire sensor is not manipulated by an attacker? What could the attacker actually do? Can we use cryptographic signatures? Can we just put some crypto into the fire sensor and then all the data that's being sent out to the control system is signed, and are we done with it? Or could there still be some manipulations? Yes.
Well, to point it out before, the sensor itself, even in normal activity, might be noisy.
Yes, there might be some natural noise already in the sensor. I guess for fire sensor, hopefully they don't trigger too often without actually having seen fire. But even if the sensor itself is running on a super secure platform and all the communication that is sent out by the fire sensor is super secure, an attacker might just, hold a lighter close to the sensor or, use a vape or whatever you can do to, depending on the exact type of the sensor, and trigger the sensor through something else that is not exactly a fire in the room. There is the maybe implicit or maybe explicit, but the intuition is that the sensor is actually, if the sensor is triggered, there is going to be a fire in the room. But there's many other ways how through physical manipulations the sensor might be triggered and by the attacker. And this is actually very difficult for the sensor itself to determine that it was incorrectly triggered. So that anything that is signed and sent out by the sensor, we can make sure that it's not being manipulated while it's being transmitted, but the signature doesn't tell us that it's actually truthfully representing that there is a fire in the room. Yeah, so this is a little bit the problem of this veracity. The reading might not really represent what we were hoping to measure with this. So what can we do there? We need to have some other approaches to try to detect whether the sensor readings we're receiving can be reasonably expected to be correct. Yeah? And there's a number of schemes that I will just bring up now, and we'll also see more of this later in the term. So there could be, for example, some kind of statistical analysis of the sensor readings in a particular measurement noise. There are approaches that are proposing to do a watermark style somehow manipulation of the things that are being measured, but by the defender to verify that at least the sensor readings are still containing this watermark. And then there's the more advanced kind of process-aware manipulation detection or attack detection that I'll talk more about later. Let me start by just with the first thing here, the statistical analysis of measurement noise. I found this quite interesting. There's also a paper which I'll cite here in a second. So the idea is here, we have a sensor that we are monitoring, and we know that the sensor is somewhat noisy, and we want to now be able to detect whether someone is either directly manipulating what is being measured, or maybe also manipulating the communication going out of the sensor, maybe placing the sensor somewhere else, or maybe even exchanging the sensor with a different sensor that is, it maybe placed somewhere else, or maybe just a different, a second sensor that is the same model, but it's just a second sensor or something like this. Yeah, we want to detect these manipulations, and the idea here is that we use the fact that sensors are also having noise in their measurements, and even that the noise that is being measured by sensors is often depending on both the environment and also the exact sensor itself. Yeah? Due to manufacturing differences, two sensors of the same model might experience different noise when they're measuring things. So the idea here is that we are creating statistics about the noise that is experienced, and then we are using these statistics of the noise. We're tracking this over time to see if there's jumps or differences in these statistical properties of the noise. Yeah, so the interesting thing here is that normally in control theory, I guess we do our best to get rid of the noise so that it doesn't influence our control. And here we are now, in particular, we care about this noise, and we want to use this information that normally is thrown away to try to detect unexpected changes in the system. And the figure here just, is just some visualization here. Let's say we normally have we have this blue distribution of noise around some mean value. And now if this distribution over time suddenly or immediately jumps to some other distribution, we might get suspicious that something unexpected happened with the system. Okay, there are several papers that were actually published on this. So the first one here is this noise print paper. I don't have a year number here, but I think that's also around 2015, 16 or something like this. So here here the authors actually, although they're calling it noise print, but actually they're not even looking at the raw sensor noise. So they're not just computing the distribution of the measured value and then the noise over time, but what they're looking at is actually they're assuming that we have a system with actually a Kalman filter. So we're back to the Kalman filter. And the Kalman filter will actually give us a prediction of what the expected sensor value would be for the next time slot. And then they see the real observed sensor value for the next time slot, and they compute the difference of the two. So essentially how far away the real sensor value is from the prediction. And then they essentially plot, or they do statistics over this residual. Yeah. While here for this distribution, the noise, you need to have some kind of, you need to compute a noise, you actually need to know what the real value is, I guess. Yeah. And if you don't have the real value, you might just average over a certain window or something like this, and then assume that the average is the true value, and then everything that is different to the average is a noise. Yeah. Here they are taking the prediction of the Kalman filter as kind of an approximation of the ground truth value that is being measured, and then they compute the distribution over these residuals. And then they apply a number of metrics or statistical features. Essentially, they do some feature engineering based on this residual noise over time. Simple things like mean, standard deviation, and so on. And they, I believe, in the end, throw this into a machine learning pipeline and then try to detect big offsets there. Let me see again. So this is the Kalman filter estimation. They do the residual calculation. And then, okay, model training and testing. So there is some model that is being trained. And I forget which exact model it is in the end, but it might just be some neural network or something. Yeah? And from what they reported in the paper, they were, for example, able to tell, then detect that, for example, if one sensor was replaced with an identical copy, but just a second instance of the same model of the sensor, they were able to tell this from the changing noise distribution. They were able to tell if sensors were, for example, just shifted somewhere in the physical environment, placed somewhere else. And overall, they had relatively low false alarm rates in their things. And I think this is a quite interesting idea, just fundamentally to start, instead of throwing away this noise information and just averaging out this noise, also using this as something that could be used for detection. Okay, so this is the idea with the noise print. Then the Kalman filter variance threshold, we already saw this in the context of the drone papers. Yeah? So here we said, so before we looked at the distribution of the residuals, and now we could also just say again, okay, we have kind of this prediction already what the sensor value is going to be. We have the true value. We are doing this tracking with the Kalman filter, and the variance represents how closely our tracking or how closely the observed values are matching our expectations. And this is what is then really happening in the autopilot or autocaptor software, that we have this threshold. And if this threshold is crossed, if we have too much variance in our Kalman filter, we'll just stop trusting the sensors and we might go into some kind of fallback mode. And I mentioned already before that this is, a default approach, I guess, also from the control theoretic side, but now is kind of unintentionally also helping us against these manipulation attacks. Then coming to defenses, if I mentioned that that if your sensor is really untrusted, in the sense that the sensor could be manipulated, and also the communication between the sensor and the system might be manipulated because it's not cryptographically authenticated, and you still want to somehow get some confidence in that the values that are measured are representing real world. A number of people propose things that are essentially like watermarking schemes, where you as a defender do something to impact a physical process in an unpredictable way, or otherwise start to inject some additional small noise, random pseudo-random noise signal next to the sensor. And then you check later if this pseudo-random noise is still present in the readings that are arriving at your controller. Yeah, so this was proposed more from engineering or control theory people and not from the security people. Or system security, computer science people, but it still is an interesting idea, I think. So, for example, let's say what would be a very simple example of this? You are worried that yes, we can talk about all the spy movies and stuff like this. So when we're talking about sensor spoofing here, it is coming up in some movies. What are these movies? Let's say I don't know, James Bond or Mission Impossible movies or something like that. Anyway, so there's sometimes this scene where you have a video surveillance camera, and then people want to evade being detected or seen on the video and surveillance camera, and then they somehow try to project some image on a screen or something like this, and then the screen is essentially monitored by the camera. Yeah. So to some degree now, all the data that is being observed by the physical sensor, the video camera, is completely replaced by something that is under control of the attacker, which is somewhat similar to the other manipulations that we're discussing here. And how could you now try to detect as a defender that someone is, fully replacing the video stream that you're observing? You could try to, anyone has any idea or maybe remembers from a video how people did detect that the video stream was being replaced?
Yeah, appended or added to that data of a certain bit string.
Yeah. Okay, yeah. So there's a suggestion here that essentially goes back to cryptographic measures to some degree. Yeah, it's a very computer science way of approaching this problem, I would say. Let me just say, so for example, in some movies, I think then people figured out that the spoofed video stream was a loop or something like this. It always showed some repeating thing over 5 minutes or something like this, and then it would be reset to the previous state. We're going more into that later as well. That's replay attacks, I guess. Yeah, but in this context, the replay attacks. But in general, you could somehow try to correlate something. Either you could detect, okay, the video is now showing us sunshine and there's clouds outside or something like this. That might be some kind of side channel information. Or as a defender, you might also do some things like you could maybe, I don't know, maybe you can remotely switch off the light in the room or something like this. And then you would expect that the light is also switched off in the video stream. Yeah? And this is what I mean here with this noise injection. If you have a capability to somehow remotely do something that should be observed by that sensor, and ideally something that is not immediately observable by an attacker that doesn't know about it, or that somehow it's a little bit hidden from the attacker, then you could try to inject certain things that should be picked up by your sensors and try to verify later if they're still arriving at your processor of the data. This is the idea that is proposed here. Of course, this is this is a control theoretic paper, so they explain it slightly differently, but this is another idea. Yes.
So if you try to break into a data center and then try to loop the camera, then you would have like some vibration checking. For example, for certain times there should not be any people in the room, and if someone steps in the room, then this is somehow measured.
Yeah, or you could even have something like, I don't know, maybe you have some audio noise or something like this that you can play in the room or something like this, and later verify if that is still in the video, if it also has audio or something like this. Yeah?
So basically,
or you have maybe some little LEDs somewhere that are looking like they would belong to a server, and they're just blinking all the time, and you use that to actually send a pseudo-random sequence, and you later verify if this is correctly temporarily lined in the video stream as well.
So basically, we assume that it is not viable for the attacker to manipulate every sensor.
Yeah, so this is why I said this is not from a system security people, the paper. Somehow this assumes to some degree that the attacker is a little bit stupid in the sense of not being able to pick up on that something like this is happening, and not being able to incorporate these things again into the spoofed signals. Yeah. So if we are now assuming an attacker that is relatively strong and knows that this is happening, then the attacker could try to extract exactly this noise signal and inject that into the manipulated data stream. Yeah, I actually see that we are already at the end of the lecture again, but I'm very happy for all the discussions that we have here. Let me, we actually just discussed this case here, detecting spoofing with specific actuation control, and we're almost done with the slide set, and I'll just continue with the slide set then next week again. Thank you for attending, and thanks for all the interactions.